Today we're going to be talking about impulse. What is it? Why is it important? And this is more in line with sports and car safety, is where we see it as being useful. Force versus time graphs, and then we'll be doing some calculations. So let's look at this picture of the baseball player. Imagine that a baseball is traveling towards the baseball player. The ball has momentum, and it is going towards the batter. What will happen to the momentum when the batter hits the ball? The momentum is going to change, right? Because when it does hit the ball, it will have a collision, and then the momentum is going to be going in the opposite direction. What causes this change in momentum is called impulse. And impulse is just simply the applied force over some period of time. In this case, it is the bat that is applying the force over some given period of time before the momentum changes. Let's define impulse. We said that it is a force that is applied over some unit of time, and it is denoted as the capital letter I equaling force times time. The impulse is equal to the change in momentum, and it is measured in Newton seconds or kilogram meters per second. Here's an example of two balls of the same mass. They are dropped onto a table. They both start off with the same velocity, and you are asked the question of which ball experiences the most change in momentum. Let's watch the first ball. The second ball is dropped. Okay, so what do we know? We know that they're both the same mass. We know that they had the same velocity. They both end up at rest. So the change in momentum is the same. We also know that impulse equals the momentum. And impulse is the force times time, equaling momentum, which is mass times velocity. So the change in momentum is the same. What then is different? The time that each ball interacts with the table. So here we had the ball interacting with the table until it became at rest. It took a shorter time to come at rest than it did for the second ball. So the ball 1 experiences a larger force with a smaller period of time, whereas the second ball experiences a smaller amount of force with a larger amount of time that force is being applied. There is an equation to show the relationship between impulse and momentum. And we are using force equals mass times acceleration. And we know that acceleration is velocity over time. And it is the change of velocity over the change in time. When we take this into account, and we move the time over to the other side, we get impulse, which is force times time, equaling m times v, which we all know that to be momentum. This is the overall equation that we note, and it is located in your data booklet. So now that you have your data booklet physically, go ahead and check it out. Make sure that it's there, and that if you need to make any notes, do so. Changing the impulse is going to change the momentum. So that's what this is telling you. If you want to change momentum, just change the impulse. To increase the impulse, you just increase the force over the smallest amount of time. Now, take a look up at the second equation, and you'll notice something like the mass times the change in velocity. What is that? So let's go ahead and take a look, and we know that force equals, that is momentum, over the change in time. So if we're given a problem we were asked to solve for the amount of force, we can do so by just having the momentum over the amount of time. Impulse can be seen everywhere, and it is really important in sports. For example, with boxing, when a person is being punched, if you extend the time of impact, it actually decreases the amount of force that your face would experience, and therefore you would be less hurt. This is actually termed riding the punch. And what you would do instead of this guy right here, he's holding his head very still, his neck is very stiff, and he's pretty much just taking all the force to his face. To ride a punch, you would actually need to relax your neck and allow your head to move back as you are being punched. That is considered to be riding the punch. And when you do that, you are increasing the amount of time that you are experiencing the force, therefore decreasing the amount of force that your face is feeling. If you were pretty much being stiff, or even heading towards the punch, you would be experiencing a shorter amount of time with that punch and the force hitting your face, and therefore you would increase the amount of injury that you could possibly have. In rock climbing, they use certain kind of rope, and the kind of rope that they use is nylon, and it's known to have a lot of stretch. So if you fall, you would actually feel the rope stretch until eventually you come to a complete stop. And what happens is, because you are increasing the amount of time that you're experiencing the force is less, which if you were using a rope that did not have any stretch, you would probably break your back. You also see impulse as being very important in racket and bat sports. When you're following through, and remember, to follow through means to do a full swing. For example, here you have the baseball player and he is doing a full swing at the baseball. Over here we have a tennis ball that is being hit back with the racket, and then we also have a stationary golf ball with the person who is going to be swinging with his golf club. When you're following through, you actually increase the time that the collision is occurring. By doing this, you're affecting some part of this equation, right? And the part that's going to be affected is the velocity. So you could get a ball that is coming at you at a slower velocity than when you hit it, you could send it going back very quickly. Impulse is also important when it comes to cars, and especially so when we're talking about the safety of us in a car. If the change in momentum occurs over a long period of time, then remember that the force of impact is small. So if you were to choose to go and drive your car into a haystack versus driving your car into a wall, what you are going to notice is that the amount of time going into a haystack, you are going to have a larger amount of time, a smaller amount of force, therefore you are going to be less hurt than if you experienced a high amount of force over a short period of time. When we're talking about safety in cars, one huge example is airbags. And when a car collides into an object, and if it hits it hard enough, the driver is still moving forward because they have inertia. Their body is still thinking that it's going forward. And it does take some time before the momentum of your body will come to rest. The airbag actually increases the amount of time that the force is applied, therefore decreasing the force that your body would experience. Another feature of cars is that the companies have actually created crumple zones, and those are located in the front and the back, and these are to absorb the amount of force that you would otherwise be taking on to your person, onto your body, if these did not exist. So the cars crumple, and because they do that, it results in an increase in collision time, and therefore, again, the force is decreased. Here is an example of a 1,300 kilogram car traveling at a velocity of 15.6 meters per second before hitting a wall. The man inside the car is 78 kilograms. The car comes to rest in 0.072 seconds, and the person continues moving forward and then comes to a complete rest at 0.112 seconds. Calculate the impulse and the force on both the car and the man. Go ahead and pause this and try to see if you can come up with an answer. Okay, so the first step is going to be to look at one of the objects. Let's take a look at the car. Let's go ahead and solve for the impulse of the car. And what we know about impulse is that impulse equals the force times time, and that is going to be kilogram meters per second. So what items do we have that would equal kilograms meters per second? When we plug all of that in, we get 1,300 kilograms times 15.6 meters per second, and that will give us an answer of this, putting it into scientific notation, 2.03 times 10 to the 4 newtons seconds. Finding the force of the car, so now we're going to take this information, and we know that impulse, which is force times time, equals this amount. When we plug in the amount of time that we know that the car comes to rest, which is 0.072 seconds, we get an answer of 2.8 times 10 to the 5th newtons, and that will be two significant figures. Now we find the impulse of the person. When we do this, we get an answer of 1.2 times 10 to the 3rd newton seconds. To find the force of the person, we have to plug in the amount of time that it took that person to come to a complete rest, and we solve for force, giving us an answer of 1.1 times 10 to the 4th newtons. With force time graphs, the area under the line is the impulse. So looking at this example here, we know how to find the area of a triangle and for a rectangle. If you were asked to find the impulse of the force graphed from 0 to 5 seconds, all you would need to do is find the area under the line. Go ahead and pause this and see if you can find the area. My answers for the triangle and for the rectangle, when I'm finding the area, is a total of 12 newton seconds. And that is my impulse for this graph. There is a relationship between kinetic energy and momentum. And let me show you how we get to our final equation to show that relationship. Using the equation of kinetic energy and momentum, I'm taking the momentum equation and I'm going to plug it into my kinetic energy equation by making v the velocity squared. And when you do that and you solve for velocity, then we can actually just take the velocity squared, which is the p squared over m squared, and we plug that into this equation. Then we get the relationship of being the kinetic energy equaling momentum squared over 2 times the mass. Collisions. Collisions are interactions between two objects, and one thing that we know is that the momentum before the collision equals the momentum after, and this is the conservation of momentum. One kind of collision is called an elastic collision, and this is when objects collide without being deformed and without generating heat. Here are some examples. So with example A, we have a ball that is moving, strikes another ball at rest, and then the second ball begins to move. In example B, we have two balls that are moving towards each other, strike each other, and then from that we have the two balls that go in the opposite direction when they were originally traveling. In example C, we have the two balls that are traveling in the same direction. However, one of the balls is obviously traveling faster, collides into the second ball, and they are both still moving, but of course their momentums will be different because of the collision. Here's an example. Consider a 6 kilogram fish that swims toward and swallows a 2 kilogram fish that is at rest. If the larger fish swims at 1 meter per second, what is its velocity immediately after lunge? Disregard water resistance. So what we remember is that the net momentum before lunge will need to equal the net momentum after lunge. So this is before the collision and after the collision. And this is also, remember that momentum is the mass times the velocity, and the mass times the velocity of after the collision. Let's go ahead and solve this. All right, so we know that we need to take into account that before the collision we have fish number 1, that is 6 kilograms, its mass, traveling at 1 meter per second, plus 2 kilogram fish right here, the little guy, and he is at rest. So he is going 0 meters per second. And that is going to equal your after collision net mass of 6 kilograms plus 2 kilograms times the velocity, which we do not know but we want to know. When we solve for this, we get an answer of the velocity being 0.75 meters per second. Now let's take that same example and suppose that the small fish is not at rest but is actually swimming towards the large fish at a 2 meter per second rate. Go ahead and solve this problem. Notice that my picture here has the direction of the fish going in the opposite direction of the larger fish. Therefore, I'm going to give it a negative value, so then that way I can remember that we do need to take those the directions into account. When we solve for this, remember we do need to say that the momentum from before is equal to that of the momentum after. Finding the before, it is going to be fish number 1's momentum plus fish number 2's momentum, equaling that of both of the fish together times the velocity of those two fish. Solving for velocity, we get an answer of 0.25 meters per second. There is another kind of collision called an inelastic collision, and this is when objects collide and become distorted and generate heat. The example below shows freight cars that are of equal mass, and one car is moving at a velocity of 4 meters per second towards the other car that is at rest. So that is experiencing a velocity of 0 meters per second. When the first car hits the second car, both cars stick together and begin to move together. And notice here that the velocity is a total of 2 meters per second. Let's do the math. We know that in an inelastic collision between two freight cars, that the momentum of the freight car on the left is shared with the freight car on the right. This is, again, remember the conservation of momentum, that the net momentum before has to equal the net momentum after. When we solve for this, we know that the masses are the same, so it doesn't even matter putting in the numbers. We can just say m times the velocity of the first object. This would give us the momentum of the first object, plus the momentum of the second object, which is at rest, therefore that value will be 0, equals the total amount, which we know the masses are the same, so we just multiply 2m, times the velocity of the two objects after the collision, which is what we're trying to solve for. When we solve for the velocity after, we get a total of 2 meters per second. The last kind of collision is called an explosive collision, and this is where two objects interact. However, before the explosion, the total momentum is 0 because neither object is moving. So here we have momentum 1 plus momentum 2, so these are the two objects, equaling 0. So before the explosion, the two objects are at rest, and then after the explosion, we have the two objects heading off in opposite directions at a specific velocity, which we should be able to solve using our nifty mathematical skills. Here's an example. A 56.2 gram tennis ball is loaded into a 1.27 kilogram homemade cannon. The cannon is at rest when it is ignited. Immediately after the impulse of the explosion, a photogate timer measures the cannon to recoil backwards a distance of 6.1 centimeters in 0.0218 seconds. Determine the post-explosion speed of the cannon and of the tennis ball. So in this case, go ahead and list what you know. What we know is that the cannon's mass is 1.27 kilograms. The distance is 6.1 centimeters. And the time that the cannon recoiled back 6.1 centimeters is a total of 0.02188 seconds. The balls mass is 56.2 grams, and that is equivalent to 0.0562 kilograms. Go ahead and try to solve this before starting the video again. Alright, so the next step is to find the velocity of the cannon. When we do this, we have the velocity of the cannon, remember, being distance over time, and so all we need to do is take the time, or the distance, which is 6.1 centimeters, divide that by the time, which is 0.0218 seconds, and that will give us a rounded estimated answer of 280 centimeters per second. When we plug everything in, we have the mass of the ball, we have the mass of the cannon, and we have the velocity of the cannon. Solving for the velocity of the ball, we get an answer of 6,323.26 centimeters per second, or 63.2 meters per second. All right, that's everything for today. Be ready to use this information in class.